So today we continue our discussion on LP modes in a step index fiber, which we started last time. Right, so basically we solved the scalar wave equation, right, under the weakly guiding approximation. We solved the scalar wave equation in cylindrical coordinates and then got the solutions. So for the radial part as a Bessel function, and then the azimuthal part as sine or cosine, right, with some integer index, right? And then where we left last time was when we apply the boundary conditions, we get this kind of transcendental equation. Right? So basically U and W depend on beta. So recall, so U was basically A times E naught square N1 square minus beta square, right? And W is A times right, and so like this, these are usual kappa and gamma, right? And so basically, just like in the slab, we had a transcendental equation. In the fiber also, we have this transcendental equation now, but in terms of these Bessel functions. And the solution to this would give me the value for beta, right? For a particular mode. So we can simplify this relation a little bit more. So here we have derivatives of Bessel functions, right? And there are many identities relating Bessel functions, trigonometric identities for sinusoidal function, right? So, for example, we use this identity relating the derivative to the Bessel function of different orders. Okay, so yeah, basically we can use these identities here, right? So the first term will cancel out on both sides. We'll just get L on both sides, so that cancel out. The remaining term, the surviving term, will be the second term. Okay, and we can use further relations like okay, so relations between different successive orders of the Bessel functions. Okay, so basically, depending on which sign you use here, plus or minus, right, you end up with two different equations depending on which sign you use, plus or minus, right? So, for example, if you use a plus sign, you end up with this equation. Okay, so that's one form of the transcendental equation. Or if you use the minus sign, you end up with okay. So basically the ratios of successive orders of Bessel functions, right? So basically for different L values, we get different equations, right? And we get different solutions. So the beta values for different L values are different. Right, so we have these two forms, right, which are both are equally valid. But typically, so for L equal to 0, we use this one. Right, so he will get J1 by J0 here, or K1 by K0. And for L greater than equal to 1, we use this one. Okay, so here we'll have a lower order ratio of a lower order Bessel function to a higher order Bessel. And so we use this one for all L values except 0, because basically the function here is better behaved. So if you have a lower order divided by higher order, basically this so this thing tends to 0 as W tends to 0, right? So basically, so when beta is close to K0 N2, which is like cut off, right? Basically the mode has gone into the cladding. At that point, this becomes 0, and for all other values, it sort of smoothly increases to finite values. Whereas here, like this goes to infinite values. So to solve the equation, this is more convenient. So that's why we use this one for all L values. But for 0, because we have a minus here, we go into negative. Right? So for L equal to 0, we use this one. Okay. And so now, just like in the slab, we can define normalized parameters, right? So for example, we define this small b, which is beta over K0, right? Which is like n effective minus right. So the normalized propagation constant, right? So recall this is n effective beta over K0. So n effective lies between n1 and n2. So beta b small b lies between 0 and 1, just like for the slab. Right. So in terms of these parameters here that we've defined, this is basically w squared by v squared. Right. Again, so recall v was basically u square plus w square is equal to v square, right? And v is the v number of the fiber, depends on the size, wavelength, and index number. Okay, so basically in terms of, so recall for the slab we made these BV diagrams, right, which are universal curves because they are in terms of normalized parameters, right? So you take any slab, you can use that equation, right, because you sort of take out the difference of wavelength and thickness and refractive index. So similarly here for the fiber also we can get universal curves BV, right, which don't depend on the parameters of the individual fibers. They are universal curves, but you can use them for any fiber, right, because, in terms of the normalized parameters. Right as v times square root of b, this one here, and then u, so we write as square root of v square minus w square, so you can write that as v times square root of 1 minus b. Right. So here basically U and W we can replace in terms of B and B. Right. So in terms of the normalized parameters, basically, so we get the same equation. We just replace U and W.
Sir, in the expression,
Yes.
beta by k naught is equal to what? In
N effective. N effective, right?
Okay.
Effective index, which we've defined before. Okay, so this is for L equal to 0. And for L greater than equal to 1. Okay, so these are in terms of the normalized parameters B and B. And so the solution of this will give us the BB curves. So again, let's see how the solutions look like. We can again sort of see them graphically. Although since they are Bessel functions, it's I guess not so intuitive or straightforward to imagine how the graphs look like. Okay, so for a given L, right, you have one particular equation for a particular L value, and so the solutions for one particular L value, there will be some finite number of solutions for that. Okay, so we'll get another index, right? So for each L, get n solutions to this transcendental equation. Right, so basically now we have two indices then. So the LP mode has two indices, one is L and then M. Right, so each mode is uniquely defined using two indices. First is the L value, right, which we saw is the angular, gives me the angular solution, like the azimuthal solution. And then for that L, I can get M number of solutions, right? So I have another index as to which solution it is. So you have two indices. So for the slab, recall it was a one-dimensional structure, right? So the refractive index was varying only in one dimension, so we got only one index. Here in the fiber, the refractive index is sort of varying in two dimensions, right? It's a 2D confinement. So we get two indices. Okay, so that's like a general rule. If you have any waveguide which has confinement in two dimensions, you get two indices. If you have only one dimension of confinement, you will get one index. Right, so this L, recall, had integer values 0, 1, 2. So M is denoted by integer values again because it's a finite discrete set, right? So we can denote them as 1, 2, 3. Okay, so as an example, let's have a fiber with B number 6. Okay, so it could be any fiber. The refractive index, contrast, and size and wavelength of operation is such that V number is 6. Okay? So you could have different fibers with different properties operating at different wavelengths, giving you V equal to 6. But as we see here, in terms of the normalized parameters, it only depends on the V number. So basically, we can plot the left hand side and the right hand side and look for intersections again, right? The same way we did for slab. So now we have, so for each L we have an equation. So for each L we have to do this, right? So we can, on the x-axis, plot as a function of V. Right, so V is fixed. So the varying parameter is B, and you know B goes from 0 to 1, right? So for example, if we do L equal to 0, then we use this top equation here. So the right hand side, if you plot as a function of B, it looks like this. Okay, so this is the right hand side. So the modified Bessel function is K. And now we've got the left hand side. Okay, so it goes like that. Okay, so at some particular value here, so the left hand side is the ratio of these Bessel functions of the first kind, J, right, J1 by J0. So now we saw that these are some points. So for example, if this denominator becomes 0, right, if the argument here is such that this is a root of the J0 function, then this will go to infinity, right? So that's what's happening here. So at this point, basically that V times square root of 1 minus B, so J0, this is becoming 0, okay? So the first root of, if you recall, so when we plotted these Bessel functions, the first few orders, right? So J0 first becomes 0 at when this becomes around 2.4. Okay, so V is 6, so you can see that at some value of B here, this argument becomes 2.4, and so that's a J0 of that is 0, so this blows up. Right, so before that we get an intersection here. Okay, so that's my first mode, M equal to 1. Right, that has the largest B value. Right, so recall again, the lower order modes have higher effective index or higher propagation constants, right? So which means the B is closer to 1. So for the lower order modes, for the higher order modes, they come closer to 0. Right, and then again it will start from here and sort of go like this until it encounters a second root of the J0 function. Okay, so this is the point where you get a second root. So here now this value becomes 5.52. which is the second root of, right? So recall, for example, J0 looks like this, right? So this is the first 0 crossing at 2.4, this is like 5.2. Okay, so we get another intersection here, look for that. Right, so you can see that basically we'll encounter a mode every time before we get a root of the J0 function. Okay, and basically those are the only two modes here. So now this one doesn't have any intersection with this stuff. right? So we have, so this is L equal to 2, right? So this will be LP, so recall this is L equal to 0, so this will be LP01, this will be LP02, okay, and the corresponding B values we can get from this. Right, so LP01 is sort of the fundamental mode, LP02 is the higher order mode. Okay, we can do a similar exercise for other L values, right? So now, for example, we can do the same thing for L equal to 1. So this is L equal to 1. So for L equal to 1, we use this equation. And so now the right hand side has a minus sign here. Okay, so that means it basically is negative values. So it looks like this. Again, this is RHS. And so now we plot the left hand side. So that will be for L equal to 1, that will be J0 by J1. Right? So for L equal to 0, we have J1 by J0. For L equal to 1, we have J0 by J1. Okay, so that sort of looks like this. Okay, so it starts from some value here, then it crosses 0 at some point. That is again, so actually it should cross 0 here, right? Okay, so again, so here now we have J0 by J1. So that will become 0 when this argument of J0, when the root of J0 is encountered, right? So at the same point, so now this will be 0. Basically, it's the inverse of this. So this load up, this becomes 0 here, right? And then it will keep going. So now it will blow up at, so at this point where, so at this point what happens is J1 becomes 0, right? So this is the root of J1. So the root here at 3.83. Okay, so when this b times square root of 1 minus b becomes 3.83, then this is blowing up. Again, before that we get an intersection here. So this is m equal to 1. Again, it starts from here and then goes like that. Right, so again it crosses 0 at the next root of J0. Right, so here at whatever, so this was 5.5 something, right? So that's where it now crosses 0. Then there's another intersection here. Okay, so now, so these are what? LP11 and LP12. Okay. So we basically keep going until we find intersections, right? So we found 2 intersections for L equal to 0, 2 for L equal to 1. Now we try L equal to 2. So again, L equal to 2 will look similar to this, right? Because we use the same equation here. The indices just go up by 1. So again, so this sort of looks like the right hand side looks like this. Yeah, again, the left hand side starts from here. It crosses 0 and then becomes, so here again it crosses 0 when you encounter the root of j1, right? So for L equal to 2, you have j1 by j2. So when j1 becomes 0, again, so here basically you're encountering this root of j1. Right, and now it blows up when, so here j2, we encounter the root of j2, so that is at 5.13. Right, again before that there's an intersection here. So that's n equal to 1. So this is LP21. Right, and that's the only intersection for L equal to 2. Similarly, L equal to 3, we have one intersection. Okay, so looks like this. The T3 one, right? Again, here it's crossing 0 when J2 becomes 0. Okay, and now if you try L equal to 4, we don't get any intersection. Okay, so these are it. So for L equal to 4, L equal to 4 and beyond, 5, 6, 7, there is no intersection, right? So that's basically the procedure. You start from L equal to 0, and then keep going up and check for solutions, right? So once you reach an L value where you don't get any solution, then for any higher L values also you won't get any solution. So there's a question: how do you obtain? You basically just plot these functions. Okay. So you can see how they look like. I mean, these are new to you because you haven't encountered Bessel functions, but like this, we are doing the same procedure that we did for the slab, right? We had a transcendental equation, we plotted left hand side, right hand side, and then looked for intersection. We are doing the same thing here, right? Instead, just we now have more complicated functions, but we can see the general form, right? So they'll cross zeros whenever the numerator goes to 0, they'll blow up to infinity whenever the denominator goes to infinity. So that's what's happening here, right? And whenever a 0 crossing, and then between the 0 crossing and the blowing up, we get a solution. How are L and M related? I mean, there is no relation as such, right? So for any L value, you can get any number of M values. There's no restriction, right? So that depends on the V number, right? So we saw that for example, V equal to 6, we have two solutions. So for L equal to 0, we have 1 and 2. For L equal to 1 also we have 1 and 2. But for L equal to 2 and 3, we have M equal to 1. So there is no relationship as such, like maybe you're sort of trying to look at it comparing to, for example, the orbitals in quantum mechanics, right? So there is some relationship between the, like for example, L runs from 0 to n minus 1 or something like that. So, but here there is no, L and M are independent, right? So for each L, you can get a particular set of M values, and there is no restriction. So depending on the V number, you'll get some number of M values. L equal to 2. No, so for L equal to 2, so recall we use this equation. So that's L minus 1 by L. So we have J1 by J2, right? So this will become 0 when J1, the numerator, becomes 0. So that's what's happening here, right? J1. And then when J2 becomes 0, then it will become infinity because we have divide by 0. So that's here and closer. Right. So, okay, yeah. So for right. So if you just want to know, so for example, if you plot for L equal to 4, you'll get something like this. I mean, actually, how it's done is like, of course, you need a computer to plot these functions, right? Can't really do them sort of analytically. But so yeah, for L equal to 4, basically the RHS looks similar like this, but the LHS doesn't cross 0 at all. So there is no intersection, right? And similar for higher values. Right, so for we see for this V number equal to 6, there are a total of 6 modes, right? LP01, LP02, LP11, LP12, LP21 and LP31. Right? So again, just like in the slab, this V number gives me an estimate for the number of modes. The higher the V number, the more modes I have. So, for example, we can do the same exercise now, change the V number, right? So, for example, now if I go to let's say V number of 2, okay? So, for example, a 3 times smaller 4, or I go to a wavelength which is 3 times larger for the same fiber. So V equals 2. So now, because the V number is smaller, we get fewer modes, right? So we got 6 modes for V equal to 6. I mean, that there's no relation, that's just a coincidence that we got 6 modes for V equal to 6. V doesn't give you exactly the number of modes. We'll see the relationship between V and the number of modes a little bit later. But so for V equal to 2, right? So again, if you do for L equal to 0 first, right? So again, curve looks like this. Right hand side is this. And now the left hand side, because the V number has decreased, right? So you can see that, so earlier the V number was 6, right? And the argument of this Bessel function is proportional to V. So now I've reduced it to 2. So you can see that the maximum value this will go to, right? So when V becomes 0, the argument will go only up to 2. Right? So actually we won't even reach this 2.4. Right? So the entire range, so here it will go only up to 2. So we won't reach this first root of J0. Right? So the left hand side will look like that. And we'll get one intersection. Right? So that's again LP01. So now you can see that LP01 will always exist. Right? Because the right hand side is some function which starts from 0 and then increases monotonically. Right? The left hand side is a function which starts again from 0 on the other side and increases monotonically. Right? No matter how small I make V. So as I make V smaller and smaller, this curve just goes down and down and down and down and down. But since this is starting from 0, there will always be an intersection. Right? So this LP01 mode always exists, no matter how small V is. Right? And you can see the smaller I make V, this intersection goes towards 0 and towards V equal to 0 more and more. right? So the mode is less and less guided. The value of B becomes smaller, but it always exists. Now, if I do for L equal to 1, actually we don't get any intersection. So now RH is like that, and now RH is again, it doesn't cross 0 again, because again we are not able to reach this 2.4, right? So it doesn't reach 0 at all, right? So there is no intersection. Right, so for B equal to 2, only one mode exists, LP01. Okay, so basically what, to completely characterize a step index fiber, right, what you can do is, for each value of V, do this exercise, find the mode which exists and find its corresponding propagation constant, right? And then plot it on the B versus V graph, right? So for a particular value of V, you find out how many modes there are. For each mode, you plot the value of B that you get, right? So you can get BV curves, right? You can see, I mean, it's just a little bit more tedious, right? But you can numerically do this, right? And people have done this because these are standard equations to solve on the computer. So you can sweep V over some range and find all these solutions for each V, plot the V values, right? So you get these BV curves, just like we had for the slab. And these BV curves completely characterize any step index fiber, right? Because I can use those curves for any fiber at all, because they are normalized parameters. Right, so we get these BV curves. Right, so we vary V. So let's say starting from 0. We've got B on the y-axis. Right, again it goes from 0 to 1. And now basically, yeah, from these solutions, we can take each mode and see how the B varies as we change V, right? So for example, LP01 is the first mode which exists, right? So that always exists, as we see here, for any V value. So even for very small V values, it always exists. So basically the mode starts existing already from V, any V greater than 0. Right, so if for LP01, if you plot, so it looks like that. Right, so this is LP01. Right, which is the fundamental mode in a step index file, right? The lowest order mode with the highest B value for a given V value. All the other curves will lie lower than this. Right, so the next mode which exists is LP11, right? So we saw that will start existing as soon as so we had curve like this, remember? So as soon as this curve crosses 0, which will happen when this J0, right? So for L equal to 1, we had J0 by J1. So when J0 crosses 0, we have a solution, which is LP11. Okay, so that starts from here. So you know the first root of, as we discussed, J0 is 2.4. So somewhere here, 2.4 LP. After this, now we have the LP11 node. Okay, so this is now 2.4048 again, right? So where J0 is the first root of J0. Right, so again, below V 2.4, only one node exists, which is LP01, right? So if the V number of the fiber is less than this 2.4, then it's called a single mode fiber. Okay, and nowadays, as mentioned previously, also for most applications, especially for example for telecommunications or something, single mode fibers are used. Okay, for considerations of dispersion, etc. Right. So how to design a single mode fiber is you want to make sure that the V number is smaller than this value. Right. So when you choose the core size and the refractive index difference, you have to choose such that the V number is less. Right. And the only mode which is supported is this LP01. Okay. So the next mode which starts existing is LP02 and LP21. They look like this. Okay, both of these have the same cutoff. So LP21 and LP02. Right, so why do these have the same cutoff? So again, where is the cutoff happening? So now here, this is J1, right? So the root of J1. So LP02 is the second mode for L equal to 0. So L equal to 0 is this equation, right? J1 by J0. Right? So that you see that, so the LP01 mode always exists, right? Once you encounter the root of J1, then the second mode will also exist, right? So remember, so basically what happens here is this LHS starts looking like this, right? So once you cross 0 here, which is the second root or which is the root of J1, right? So remember we are plotting J1 by J0, right? So this is J1 by J0 for L equal to 0, right? So it blows up first when J0 root is encountered, which is at 2.4. And then it becomes 0 when J1 root is encountered, right? And after that, you get the second mode. So the first mode you already got here. The second mode, LP02, you will get once you cross the 0 of J1, which is what is happening here, right? So that is LP02. LP21 again. So that's L equal to 2. So we use this equation, that will be J1 by J2. Right? So again, that looks something like this. And so that will cross 0 when J1 crosses 0. Right? As soon as it crosses 0, we'll have a mode, the LP21. Okay, so both of these will have the same cutoff, basically where the J1 root is. Right, so again, recall the Bessel functions, how they look like. So J0 is the only one which is non-zero at 0. Right, so that's J0, and then J1 looks like that, right? J2 looks like that. 0, right? So all the for all L greater than 0, they actually start from 0. So they are actually 0 at. So for example, when B equal to 0, they are actually 0, right? But this ratio, the limit of the ratio is actually finite, right? Which is why this curve starts from finite value, right? So they become, so the relevant root is when they become 0 next. So when J1 becomes 0 next, so this is, so okay, J0 becomes here at 2.4, J1 here becomes at 3.8, J2 here becomes at 5.1 or something. Right, and then we have here the next mode will be LP12. Right, so this will happen when again, so L equal to 1, here we have J0 by J1. So the first root gave me the first solution, the second root of J0. So when J0 crosses 0 again, that happens here at 5.52. Okay, so here J0 second root happens. After that you get LP1. Okay. Similarly, then higher order nodes, right? So this is LP22. Right, so 2 will happen at the second root of J1. So this is J1, it crosses 0 again at 7 point something. Right, so J1 here crosses 0 again at, so this is 7.01. Okay, so basically from the roots of the Bessel functions, you can find the cutoffs for different modes, right? So the point at which these modes start existing, they are known as the cutoff value. So this is VC cutoff for, so this will be cutoff for 1, 1, right? So LP01 has no cutoff, it always exists. So they only exist if B is more than that cutoff value, right? And so for example, B is inversely proportional to lambda. So this will correspond for a fixed fiber for a given pore size and index difference. If we vary wavelength, right, this will correspond to some cutoff wavelength. And the mode will only exist for wavelengths smaller than the cutoff wavelength. Right, so anyway, so these curves are universal, right? They don't depend on the, if, so for a step index fiber, these curves are universal. Right, so we can, if you have any general given fiber, if you know its core size and index difference and the wavelength of operation, you can calculate the V value, and then from this plot, for that V value, read off the B value for whatever mode you want, right? And from the B value, you can get the propagation constant, right? So you can do this for any fiber. So these curves are universal. How do we plot these curves, right? So each point here, we are getting from the solutions to these curves, right? So for each V value, you take some V value, right? Then you have to plot these functions, right? Find the solutions. The solution will give you B. So you plot the corresponding V, right? So you choose each V value from those solutions. You find the B values, and then you just plot them. And so for each mode, you get a different graph. Right. So again, how do we calculate these cutoff values? Are basically from the roots of the Bessel function.
Excuse me, sir. So suppose we design a waveguide with V number equal to 4, and let's say I launch light, then does that mean that all the 4 modes, that is LP01, LP11, LP21, and LP02, get excited?
Again, so recall which modes gets excited by what amount depends on this overlap integral between my input launch profile, right? So remember when we were discussing properties of modes in the slab waveguide, right? Similar, those properties of modes hold for any waveguide, right? So each of these will have some particular mode profile. We haven't looked at them yet, but just like in the slab, different modes have different mode profiles, right? Similarly, here all of these will have different mode profiles, right? So we'll see how they look, right? So for example, in the radial direction, like LP01 maybe looks somewhat like a Gaussian function, right? I don't know. LP02 maybe like looks something with a 0 in the middle, right? So they have different mode profiles. Again, right? So now whatever input profile I'm launching here, right? So this is some input profile that I launch, right? So you calculate the overlap integral of your input profile with some LM, whatever mode profile of the mode you're looking at, right? So this overlap integral will give you some value, right? Which is the coefficient of or the power in that mode which is excited, right? So yeah, in general, all modes will be excited with different strengths, right? Depending on what your input launch profile is. Right, so for example, if you tailor your input profile to look more like the mode you want, so the overlap will be maximum with that mode. With this mode, the overlap will be smaller, right? So most of the power will be launched in this mode. Okay. So again, these mode cutoffs, right? Just to sort of formally list them. So they happen whenever. So in the transcendental equation, we have some LHS equal to RHS. Whenever this LHS crosses 0, right, we get another mode. Right, so basically for L equal to 0, the transcendental equation was, so this one was J1 by J0 for L equal to 0. So for L equal to 0, LHS looks like J1 by J0. So which means cutoffs are given by roots of J1. Right, so the first M equal to 1, so this is LP01, right? So that's the first root of J1, which is just 0, right? So 0. So the cutoff for 0, 1 is 0 or no cutoff, right? It's always 0. Right, again, M equal to 2 will be when the next root of J1, which is at 3.8. Right, so M equal to 3 will be the next root, which is 7.01. Okay, and now for L, for other values of L, we have L minus 1 by L, right? So for example, for L equal to 1, we have J0 by J1. So now we are looking for roots of J0. Right, so cutoff for LP11. So magnitude 1 will be when J0 becomes 0, that's at 2.4. LP12 will be the next root, which is 5.52 something, right, and so on. So for any so for values greater than or equal to 2, basically we just look for roots of JL minus 1. Right? So whenever JL minus 1 becomes 0, that gives me the cutoffs. So for the mth mode. So mth root will give me the cutoff for them. Of course, we ignore the 0 root, because for L greater than or equal to 2, actually JL0 is 0. But we ignore that because that doesn't give me, as I said, this ratio, both are 0, right? We ignore this because at 0, both are 0. So JL minus 1 by JL, both are 0 at BC equal to 0. And the ratio is actually finite. So we ignore that first 0 and then look for the successive roots of JL minus 1. Okay, we'll stop here. Okay, so next class first we'll look at the mode profiles, how these different modes look like in the cross section XY plane or R5 plane. Right? And then we discuss some of further properties like how much power is carried and what is the fraction of power in the core for different modes.